Suppose I'm given this function, y equals 1/2 x squared times the square root of 4 minus x squared, and I want to find the derivative. Well, let's break down this function. Let's first consider a couple places where this might behave in a noteworthy or special way. I can see that if x is 0, the function is going to equal 0, and if x is plus or minus 2, I'm going to get a 0 factor from this radical expression. So at plus and minus 2 and 0, this function will hit the x-axis. I can also see if x is bigger than 2 or less than negative 2, this function is going to be undefined. I won't get a real number because I'll end up with a negative under the radical. So with that in mind, let's take a look at the graph. Here we are in Desmos, and I can see, let's take a closer look there. As expected, this function stops existing past negative 2 or positive 2, and it hits 0 at each of these three places. We can see that the slope is vertical here on the left, slope approaching positive infinity. We hit a 0 slope right around this location, 0 again here. The slope goes through negative, back up, the slope is positive, we hit 0 again, and then we approach a slope of negative infinity. So those are features we expect to see in our derivative, which should come down from positive infinity through 0 here. We're going to have negative slope, come back through 0 here, positive slope, so we have a positive value to the derivative. We hit 0 again here, and then dive off to negative infinity. So let's see how that works out. Let's first break up this function a bit into parts that we can handle more easily. I'm going to take the 1/2 and just pull it out. This 1/2, if I have a scale factor like this, if I doubled this function, everything would just be twice as big and twice as steep. So I don't need to worry about that. Now I see that I have x squared is one of my functions, and the other function, we can start making this more amenable to derivative taking. I will call this 4 minus x squared to the 1/2, rewriting the square root as a fractional power because that allows me to use my power rule. So we see we have a product of two functions. We're going to need to use the product rule. And then on this second function, I have a function inside of the square root, so I'm going to need to use the chain rule on the second function. So let's give some names to these. I'll call this first function f of x and the second function g of x, and those are multiplying each other. So we know that the derivative y prime is going to be 1/2 f prime of x times g of x plus f of x times g prime of x, just using the product rule there. So let's figure out those component parts. We bring down the 1/2, inside stays the same. Power becomes a negative 1/2 because we're subtracting 1. And inside that function, we have a 4 minus x squared. That has stayed the same. But now we want to multiply by that derivative of the inside. 4 is a constant, so the derivative is 0. But this derivative is going to be negative 2x to the first. So we have our two parts here, two derivatives that are part of the product rule. Now let's write out the whole thing. Simplifying that a bit algebraically, we can see the derivative here in Desmos. We have 1/2 out front, 2x times 4 minus x squared to the 1/2, minus x cubed, 4 minus x squared to the minus 1/2. Notice that these leading powers of x are odd powers now. We have a mirror symmetry here, an even function symmetry for our initial function, and we have odd symmetry, so f of x equals minus f of minus x for this derivative function. And it has exactly the features we described in the beginning. It dives down from infinity, crossing 0 here at the peak of the red function, approaching a maximum negative slope right about here, passing through 0 because we have 0 slope on the red function, and then just mirrored opposite behavior on the other side. So that is how we take the derivative of this product. If we look at some features of the initial function, we can also see that it is the product of this parabola and this circle. Notice that if I multiply that parabola and circle, I'm punching in, basically, the shape of the circle by multiplying these two functions, which are pinched towards 0 at these 3 points. You might want to recall, if this is not familiar to you, that for any circle, I can describe the top half of the circle as the square root of r squared minus x squared, and then I can just vary the radius there. So, point of review, that is the equation of a top semicircle.